2 kilogram mass going at 3 meters per second, hitting the ruler and sticking to it. So it's stuck to it. So we were trying to illustrate this. This is an example of a situation where you conserve linear momentum and angular momentum, but you don't conserve kinetic energy because it's an inelastic collision. Okay? So it's a collision taking place. So for that one, we had to find that the center of mass changes over here. So we had to find the new center of mass. We had to find the total moment of inertia about that new center of mass. So then we wanted to find what's the total velocity of the center of mass of the system after the collision was 0.5 meters per second. We found the omega final to be 0.31%. Loss of kinetic energy was 75.5% loss. And V total at the top point was 1.0735, which is more than twice V center of mass. Because twice V center of mass is 1, right? 2 times 0.5 is 1. So this is barely a little bit faster. So what that means is this is similar to like car in snow, where it's spinning faster after the collision. It's spinning faster than translation. And we said that that's the reason behind that is because this thing is hitting it at 0.9 meters. The picture is not drawn to scale here. 0.9 meters. This one is 4 meters, so it should look something like this. This one is probably going to be something like 1, so it's going to be something like this drawn to scale. So if it had hit it, if the 2 kilogram mass had hit it closer to the center, then the omega would have been less than 0.31, and then the V total at the top would have been less than twice V center of mass. So it would have been more like car in rain, right? So it depends where you hit it. Okay, so now I want to do the elastic version of this problem. Let's say the 2 kilogram comes, hits it, and bounces back perfectly elastically. Okay, so I want to ask, after the elastic collision, the 2 kilogram mass might bounce backward or might go forward but slow down. So it's going to go like this. We can call it V1. And then the ruler is going to be V center of mass. This one, the difference is the center of mass is not going to change because it's not sticking to it. It just hits it and bounces back, and the ruler goes forward. So the center of mass doesn't change, so it goes V center of mass, and then it has an omega final. So I want to know what is V center of mass, what is V1, what is omega final. So find out those 3 unknowns. You don't have to find percent loss of kinetic energy because there's no loss of kinetic energy. So we won't ask that. But I'll ask what is V total at the top point. Now what do you think if we make it a prediction, what is going to be the V total at the top point? Let's make a little quick prediction here. Is it going to be more than 1.07 or less than 1.07? Kind of an interesting thing, huh? Okay, how many say less? How many say more than 1.07? Okay, 2, me and him. 2 people say more, less? Nobody. Anybody else want to come on board? More? Why do you think I say more? Elastic, pew, like that, right? You impart more impulse to it. It's likely that it's going to spin faster after you impart impulse. So when you spin faster, the top point is going to be moving even faster, you see. So I think it will be more than 1.07. So I'll just guess a number here, let's say 1.25. And if it's equal to that, then you guys owe me lunch. Okay? Okay, so let's solve the three variables here. We gotta now this time we gotta conserve linear momentum, angular momentum, and kinetic energy of the system. Okay, linear momentum, P initial. So linear momentum, that's 2 times V. No, the initial linear momentum is 2 times 3. Right, so that's 6. The final linear momentum is 2 times V1 plus, and then the mass of this one is 10 kilograms plus 10 times V center of mass. So now, since they are no longer stuck, they are two distinct objects. You have 2V1 plus 10 V center of mass. I can divide this by 2. Three equals V1 plus, so this is my first equation here. I'm going to get 3 equations and 3 unknowns and then solve that system. Then I'm going to conserve angular momentum. Li equals L final. What's the initial angular momentum? Okay, now for this problem we don't have to find the new center of mass. The center of mass doesn't change. So the initial angular momentum is simply just 2 times 3 times 0.9. Remember MVH. So the angular momentum is the mass times the velocity times the vertical height from the center of mass. The center of mass is not changing in this case. So 2 times 3 times 0.9. The final angular momentum is 2 times V1 times 0.9. Right? Plus this one has an angular momentum, I omega. It's rotating, so it has angular momentum, I omega final. So we could do here, this is 6 times 0.9 is 5.4. 2 times 0.9 is 1.8. And then the moment of inertia of this is 1/12 ml squared, right? It's spinning around its center. 1/12 m, which is 10 kilograms. And the length is 4 meters. So 1/12 ml squared times omega final. So that's going to be 16 times 10 is 160 divided by 12. 160, what's that? 160 divided by 12. That goes in once. 3, right? 0.4. So 13.33, right? So 5.4 equals 1.8 V1 plus 13.33 omega final. So here's my second equation. Here's my first equation. Then I get my third equation from the kinetic energy conservation. Kinetic energy initial equals kinetic energy final. The initial kinetic energy is half times 2 times its initial velocity, which is 3 squared. The final kinetic energy is equal to 1/2 times 2 times V1 squared plus 1/2 times. Okay, now here's where you got to be careful. When you do the kinetic energy, this one has a translational kinetic energy. The ruler has a translational kinetic energy and a rotational kinetic energy. So the ruler has 2 kinds of kinetic energy. So 1/2 times its mass, which is 10 kilograms, times V center of mass squared, plus 1/2 times its moment of inertia, which was what? 13.33 is the moment of inertia, right? So 1/2 times its moment of inertia times omega final squared. 1/2 I omega squared.